Hello guys, today I am going to teach about ROLLE'S theorem. This theorem comes under the mean value theorem of real analysis. So let's get begin. First we write the statement of this theorem. Let fx be a function which is defined on the closed interval ab, then defined on ab, then if satisfy the given three properties, which is fx is continuous in the closed interval ab and fx is differentiable in open interval ab. In the third property, fa is equal to fb, that is the function value at endpoints must be equal. Then the theorem says that there must exist a point say c from the open interval ab such that m dash c is equal to 0. We can understand this theorem by graphical method very easily. So we take an example of a function such that the graph of this function is like that. Then this is the point a, this is b, x-axis, y-axis, and the origin point. So here we can see that the value of fa and fb are equal. Here this point is fa and also fb. So this come from the third point where fa must be equal to fb. Also we can see that this graph is continuous at each point from the closed interval ab. Also this curve doesn't form any sharp end, so this will be differentiable at whole points except at the end points, because at end points there can be infinite number of tangents, so at end points the function can't be differentiable. Then by theorem it says that there exists a point c from the open interval ab such that the derivative of function at that point must be equal to 0. This means that at any point from the curve, the tangent at that point must be parallel to the domain where it is x-axis. So here we get a point c such that the tangent at the curve at c is parallel to the x-axis. So this is the graphical method of ROLLE'S theorem. Now we are going to take some example and verify whether it satisfies the ROLLE'S theorem or not. We will take here 4 example. The example number 1 is as fx is equal to 3x raised to the power 4 minus 4x square plus 5 in open interval minus 1 to 1. In this second example, fx is equal to sin x and the interval defined for this function is 0 to pi. The third example, fx is equal to 10x in interval 0 to pi. The fourth example, fx is equal to modulus of x in the closed interval minus 1 to 1. So these are the 4 examples we are going to verify the ROLLE'S theorem. First we know that the polynomial function and the trigonometric function containing sin x or cos x and the exponential function, these all three functions are differentiable and continuous. continuous in whole R, that is whole real number. We can define polynomial function as if x is any variable, then fx must be like say c1 xn, or we can define a polynomial function like that it contains a variable x raised to the power either 0, 1, 2 and dot dot dot, that is all natural number and 0 also. If the variable contain as power these numbers, then this function will be called as polynomial function. We can take an example. Actually, this is the example of polynomial function where the variable is x and it has power 0 and all the natural number. Here 4, 2 and here we can write as to the power 0 and it will be equal to 1. So this is the example of polynomial function. Now we are going to verify the Rolle's theorem for these examples. Example number 1. As this is a polynomial function, so it will be continuous and derivative in whole R. So first two properties of Rolle's theorem are satisfied. For this third property where fa equal to fb, so fa is equal to minus 1, so f minus 1 we have to find, we have to put minus 1 in the place of x. So 3 into 1 minus 4 into 1 plus 5, it will be equal to 4, and f1 that is fb, we have to put 1 in the place of x, so 3 into 1 minus 4 into 1 plus 5, it will be also equal to 4. So f minus 1 is equal to f1. So third property of Rolle's theorem is also satisfied. So by theorem there must exist a point C such that derivative of that point is equal to 0. So first we have to find f dash x for this example number 1. So it will be equal to 12x cube minus 8x plus 0. So by theorem f dash c must be equal to 0. So if we put c in the place of x here, 12c cube minus 8c is equal to 0. C we have to take common c, 12c square minus 8 is equal to 0. So c is equal to 0, or c is equal to c square equal to 8 by 12. This implies c is equal to plus minus 8 by 12 or equal to plus minus 2 by 3. C is equal to 0 or c is equal to plus minus 2 by 3. Both the number belongs to, that is c is equal to 0 and plus minus 2 by 3. Both these numbers belong to the open interval minus 1 to 1. So all the property of Rolle's theorem are satisfied here. So this example number 1 satisfy the Rolle's theorem. Now we are going to verify the second example, which is fx equal to sin x in 0 to pi. We know that the trigonometric function containing sin x is continuous and derivative in whole R. So the first two properties of Rolle's theorem is satisfied for this function. So the third property where fa equal to fb, we have to check that here fa is equal to f0, so we have to put 0 in this function sin x. So sin 0 is equal to 0, and fb, which is sin pi, where f5 is equal to sin pi, which is also 0. So fa equal to fb, third property also satisfied here. Now we must get a point c such that f dash c is equal to 0. So we have to find first f dash x. Since fx is sin x, so derivative of sin x is cos x. Now f dash c is equal to 0, that is cos c is equal to 0. This implies cos c is 0, c must be pi by 2, which belongs to the open interval 0 to pi. So all the properties of Rolle's theorem also verified for this function. So this function satisfies the Rolle's theorem. Now we are going to verify for the third example where f is equal to 10x in 0 to pi. We know the graph of 10x is like that, minus pi by 2, pi by 2, pi, 3 pi by 2. Then the graph of 10x is like that. We can see that the graph of 10x is not continuous at pi by 2, that is, it is not connected at pi by 2. But the given interval for this function fx equal to 10x is 0 to pi, so this function will be not continuous at this given interval. So this function can't satisfy the Rolle's theorem. Also for this example we can solve by graph, where the graph of modulus function is like that. Number 4 example, graph of modulus function is like that, where this is x-axis, this is y-axis, and this is the point origin. We can see that this function is continuous at whole r, but is not differentiable at the point 0, that is at origin, because this curve makes a sharp end at 0, so this will be not differentiable at 0. So also this example number 2 not satisfy the one property of Rolle's theorem, which is fx is differentiable in open interval. So this example also not satisfy the Rolle's theorem. So that's it for today. Thank you.